We are Group 13, and this is our project DoorVision, a facial recognition home security system. On our team is Laisha Antonor on software, Dawson Beach on hardware, Kalani DaCosta also on hardware, and Evans Goff on software and our team lead. We designed DoorVision to provide a convenient but effective home security device, since less than half of Americans own any type of home security system. Our project is made up of two parts: a physical device to be mounted on a standard front door, and a mobile application used to monitor and control the device. DoorVision works by checking every face that approaches the user's front door. If that face matches a Face ID stored in the device's database, it unlocks the door. Otherwise, the door remains locked. The door can also be unlocked through a keypad code. To use DoorVision, first the user must create an account and scan their face through the mobile app using their phone. After the face is logged into the system, whenever they approach their front door, it will automatically unlock by triggering a servo motor to turn the deadbolt.
For our MCU, we chose the ESP32P4M3 module. The ESP's RAM and clock speed allow for quick face recognition and support high resolution camera processing at about 30 FPS. This MCU also comes with light and deep sleep modes. Our project would utilize the light sleep mode since the system will need to be continuously running for multiple weeks before recharging. As part of the hardware system, we're using the IMX219 camera module with an 8 megapixel resolution. It has strong performance in low light environments and will be used to record and scan faces as people approach the door. We're also using the OPT3001 light sensor paired with an eye safe white LED used to illuminate the area in front of the door during the night or moments of low visibility. Next, we're using the VL53L1X motion sensor, which plays a large role in power management since it's responsible for waking the system from light sleep mode and sending it back into sleep mode. The motion sensor also has its own low power mode. In this mode, it can detect up to 4 meters. While the entire system is in light sleep, low power mode, if the motion detector is tripped by sensing motion within 3 feet, it will wake the entire system in time for the user to seamlessly approach the door and unlock without delay.
A simple 10-digit keypad is also implemented as a backup to the facial recognition system. If the camera system should ever fail or the user wants to unlock the door without scanning their face, the keypad will also trigger the servo motor to unlock the door. Next to the keypad is a RGB LED to display the unlock status to the user. A 3D printed enclosure will be used to house all of our components. The enclosure consists of three parts: the exterior main enclosure, which includes a back piece, and the interior deadbolt cover. Our current iteration of the enclosure has some errors, including the keypad button holes being too small and the main enclosure being too narrow. These will be fixed in the second iteration. A mobile app is used for remote control of the system. The app's features include live camera footage, management of authorized users, remote unlocking and locking of the door, and an activity log. The app utilizes Swift, which is Apple's native coding language. Swift was chosen for its built-in database using SQLite and its security features such as Face ID and Touch ID. Our system communicates with the external hardware and requires a language that can store and process data in real time while maintaining performance.
The three key engineering specifications used to validate our current design and demo are the light sensor reliably triggering on the white light LED when the ambient light levels are below 25 lux, the motion sensor accurately triggering at distances of at least 3 feet, and a facial recognition confidence interval above 65% for a registered user. To demonstrate the light sensor specification, we recorded 10 trials of gradually blocking light from the sensor while monitoring the console output displaying the measured lux level. The light level that triggers from the LED to turn on was then recorded for 10 trials. To demonstrate the motion sensor specification, we measured out 3 feet away from the motion sensor on the ground with a tape measure and gradually approached the sensor. For a quick and easy visual verification, we programmed the RGB LED to turn blue when the sensor noticed something within its range that would trigger the system to wake from sleep mode. We then recorded the distance on the ground and the console output from the motion sensor and recorded its accuracy. This process was recorded 10 times. To demonstrate the confidence interval specification, The facial recognition program outputs the certainty or confidence in a percentage that the face it currently sees matches 1 in its database. We registered a user approaching the camera and recorded the interval 10 different times. Next up, we have a video of a user registering their Face ID with the device's camera. In the middle is a screen recording of what the user would see on their phone when they begin registering a new user on their app. On the left-hand side, you can see the live video of the user scanning their face, and on the right is the console data showing that the face is being recognized. All the user needs to do is rotate their face in front of the camera until the camera captures 6 samples. You can see in the live video that every time a sample is captured, the LED flashes green for user feedback. On the right, you'll see that once all 6 samples are gathered, the user has finished the enrollment process and is ready to use the device. Next, we have a video of a successful unlocking. Here's a demo video of a user successfully triggering the unlock sequence, as shown by the blinking green light. Since this user is already enrolled, the camera recognizes them and flashes the green light. On the right, you can see the console log detecting a face, and next to it, the percentage of how certain it is based on the detection. Next is a face scan test for an unregistered user. Since this user hasn't scanned their face to create an account, the light will not flash green. On the right, you can see the console display the text unknown face. This will be the output whenever the system doesn't recognize the face it sees. Currently, it is possible for false negatives, a known user being detected as unknown, but during testing, after a few seconds or moving your face around, the camera will recognize the face. During testing, there have been no false positives, an unknown user being mistaken for a known user. Here we have the motion sensor test. For the sake of this demo video, a 3-foot long charger was used to represent the distance the sensor should trigger the LED to turn blue. In the top left-hand side is the recording of the console log during the test. The light is set to turn on when the motion sensor detects movement within 915 millimeters, or 3 feet. When there's nothing moving close by, the sensor outputs data near its maximum distance. Finally, we have the light sensor test. To prove the light sensor reliably turns on at light levels below 25 lux, we slowly blocked the light sensor until it triggered the white light LED on. Here are the results from our testing. Across 10 tests from a registered user, the average confidence level was only 63%. Shown in yellow, only 3 of those tests had enough certainty to trigger the system to unlock the door. To improve this, we will test multiple changes to the software to see what grants the greatest improvement without sacrificing accuracy. Our current plan is to implement having the user register more than 6 face scans before becoming fully verified, as well as scanning their face in different types of lighting. By giving our model more face data to work with, it should improve the confidence level per scan. For the light sensor test, we recorded all the light levels that cause the white light LED to turn on. The LED is hard-coded to turn on at any lux level below 25, so this data mainly reflects how often the sensor checks the light level. Its average of 22.12 validates our design, but to bring the sample number closer to 25, we will increase the sampling rate of the light sensor. Here are the results from the 10 motion sensor tests. Since the sensor outputs in millimeters, we converted this table to feet for a clearer representation. During this test, we had the user walk up to 3 feet away from the motion sensor, as marked out by a tape measure. We then recorded the sensor's data and repeated. Across the 10 tests, the average distance that the sensor output as 3 feet, or enough to trigger the blue LED, was 2.91 feet, with an average accuracy of 97%. Like the light sensor, these numbers are also a reflection of the sampling rate of the motion detector. but due to the extremely high accuracy, we have decided to leave the sampling rate as is. Overall, our project is on track and meeting the desired specifications. In the following weeks, we will continue to improve both the hardware and software designs in this project. Our main priorities are redesigning the enclosure to better fit our components and improving the camera system's confidence in detecting and differentiating between faces.